Now we'll consider astronomy of the medieval period. The medieval period consists of a series of times, starting with the Middle Ages, after the end of the Roman Empire. The early Middle Ages, or the Dark Ages, run from about 500 to 1000, and then we'll follow the ascendancy of Islamic astronomy from 800 to 1400. The Islamic Empire was crucially important because during the Dark Ages in Europe, it was the only way that preserved and transformed ancient knowledge in the form of the Greek and Roman scripts. Then we get to the rediscovery, or Renaissance, where European civilization finally recovers in the high to late Middle Ages, setting the stage for the Copernican revolution and recasting the ancient tradition of the Greeks. After Ptolemy, who died in 170, not much new original astronomical thought came from Alexandria. There was some scholarly work, but it was not original. Greek astronomy, however, widely diffused into Jewish, Indian, and Persian traditions, and the interest in astrology and calendars continued. Very importantly, and only talked about briefly in this course, Indian or Vedic astronomy brought new mathematics. Mathematics developed under the Indians with the idea of using number systems more precisely, developing power series to calculate fractional numbers accurately, sine and tangent functions, and many other innovations. They also replaced the eccentric and epicycle system in the Ptolemaic cosmology with two epicycles, which were not concentric. There was some Jewish work on calendars too, in the years 300 to 400. And finally, importantly, there were crucial Persian translations of Greek work which formed the source material for the Islamic scholars that would follow. The Roman Empire fell. It had its greatest extent at the ascendancy of Diocletian in 284. But in 476, Romulus Augustulus was deposed, the warring tribes fell, the Goths took over the outer regions, and a combination of a failing economy, decadence, corruption, and we think climate change and disease led to the fall of Rome. In reflection, Rome at its height managed audacious feats of civil engineering and had an enormous bureaucratic state. Remember, they were able to run an empire with military precision over distances of thousands of miles at a time when it would have taken months to travel the extent of the empire. That's extraordinary. But among the Romans, there seemed to be little interest in science and theories or knowledge for its own sake. And so, when the Rome civilization fell, there was the loss of libraries and ancient texts at a time when usually it took a monk a year or more to write or transcribe a single book. The Greek language was largely forgotten, and even the complexities of Latin were reduced to a primitive form of Latin. Early Christianity was also hostile to pagan learning, which included astronomy and astrology. Across Europe, the standard of living and life expectancy dropped significantly. We're so used to time marching forward and progress being continuous. Every generation, every civilization is better and more knowledgeable and richer and smarter than the one before. It's not always true. There are times in the history of the world when knowledge, when progress, when the cost and standard of living have gone backwards. And so, this period of time, the Dark Ages, was a tremendous decline in cultural sophistication, and it lasted a long time, almost 500 years. Here we have a painting to sum up the chaos and horror of the fall of Rome. We can remind ourselves why we miss the Romans, because even though they were militaristic and kicked a lot of people around during their time, they did leave us with some important things.
They bled us white, bastards. They'd taken everything we had. And not just from us, from our fathers, and from our fathers' fathers.
And from our fathers' fathers' fathers.
Yeah.
And from our fathers' 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 fathers.
All right, Stan, don't labour the point. And what have they ever given us in return?
The aqueduct?
What?
The aqueduct.
Oh, yeah, they did give us that. That's true, yeah.
And the sanitation.
Oh, yeah, the sanitation, Reg. Remember what the city used to be like?
Yeah, all right, I'll grant you, the aqueduct and sanitation are two things the Romans have done.
And the roads.
Well, yeah, obviously the roads. I mean, the roads go without saying, don't they? But apart from the sanitation, the aqueduct, and the roads...
Irrigation, medicine, education,
Yeah, all right, fair enough.
and the wine.
Yeah, that's something we'd really missed, Reg, if the Romans left.
Public baths.
And it's safe to walk in the streets at night now, Reg.
Yeah, they certainly know how to keep order. Let's face it, the only ones who could in a place like this.
All right, but apart from the sanitation, the medicine, education, wine, public order, irrigation, roads, a fresh water system, and public health, what have the Romans ever done for us?
Brought peace.
Oh, peace! Shut up!
An important figure at the beginning of these dark times was Boethius, born just after the last emperor was deposed by Odoacer. He was a court official under Theodoric, the king of the Ostrogoths, which was one of the tribes that overran the empire. He wrote Consolation of Philosophy and also extensive commentaries. He also tried to reconcile the Homan See, or the early Catholic Church, with the Eastern Empire and somehow preserve the learning of the Greeks before it was lost forever. However, he was executed for treason, so his attempt did not last very long. And now we come to Islamic astronomy, which is an important part of the through line to the modern age of astronomy, at a time when little original astronomy was being done. The Prophet Muhammad began to write down the Quran in 610, and by the time of his death, the Arabian Peninsula had been united as a single political and religious entity. The rapid spread of Islam brought learning of the Greeks and other cultures, because the Islamic culture respected other knowledge. Islam itself presented three challenges to astronomical thought. They were to do with times and festivals. One was to set the month and times of fasting, the Ramadan, and the other was to set the times of the 5 required daily prayers that occurred at the beginning of twilight, when the sun's at the zenith, when the shadows are the same length as object casting shadows, from sunset, and then halfway between sunset and early twilight. They also had to determine quite precisely the direction for prayer towards the Kaaba in Mecca. And so, from early days in the Islamic Empire, they established the office of mosque timekeeper, and astronomers throughout the Islamic Empire actually had quite good and respectable jobs. There was respect for learning. The early caliphates were nothing like some of our stereotypes of the caliphates of more recent Arab traditions in unfortunate circumstances. These early caliphates were vibrant and tolerant cultures, open to new knowledge and to travel and to new ideas. There were major works at translating work from Greek and Syriac that were carried out in Afghanistan. Harun al-Rashid began to collect both scholars and manuscripts in Baghdad and founded one of the world's first great libraries after the Great Library of Alexandria, called the House of Wisdom. It was a library and an academy, essentially a university, and was the most famous of several of these centers. Under al-Mamun, the House of Wisdom reached its peak around the year 800, and there was an extensive body of works translated into Arabic. If you could speak Arabic, you had access to work by Greeks, Persians, Indians, Chinese, even Babylonians and Egyptians. An incredible resource. This was a vast intellectual empire bringing together all of these conquered people. And Arab science begins as the sum of these disparate ingredients. Early Islamic culture had a great respect for learning and knowledge. This image is a translation of an Egyptian treatise into Arabic on astronomy. It has rising and setting times, the altitude of the sun, shadow lengths. Science and mathematics progressed under these people, and we'll pick some of the famous characters that advanced the cause. Al-Khwarizmi, who died before 850, was the chief astronomer at the House of Wisdom. He's best known today for his book on algebra. He had tables of sine, cosines, and tangents, and he also revised Ptolemy's book on geography and wrote the oldest treatise on the astrolabe. Al-Battani from Syria was another one to rely on Ptolemy's methods, but he improved on Ptolemy, getting a better value for the obliquity of the ecliptic, or the tilt of the Earth's axis relative to its orbit around the sun, and thereby deriving better positions for the sun. he stressed that science depended on observation as a test of theory, which is a completely modern idea of how science works. Another major figure is Ibn Yunus, who did major work on determining the direction to Mecca from the sun's altitude, and made an exact science of determining the times of prayer that Islamic culture requires 5 times of its people. He also made precise definitions of twilight and calculated for the first time the atmospheric refraction of sunlight at the horizon. A very major character in this chronology is Ibn al-Haytham. He actually gave us a version of the scientific method completely recognizable to scientists today. He said the duty of the man who investigates the writing of scientists, if learning the truth is his goal, is to make himself an enemy of all that he reads and attack it from every side. He should also suspect himself as he performs his critical examination of it, so that he may avoid falling into either prejudice or leniency. This is a powerful defense of the skeptical vein of thought that's at the heart of the scientific method, and also the definition of objectivity, of removing yourself from the work so as to look at it dispassionately. He's best known for his work on optics, and his book De Aspectibus had a theory of vision, and this is the first time in the history of science that we have the eye defined as an optical system, the understanding that light travels in straight lines, the basic mechanics of refraction and reflection. He also observed a solar eclipse with a camera oscura, which is like a pinhole camera built into a building. He was very influential in later European Christian criticisms of Ptolemy's cosmology. The Almagest was abstract geometry, not really an explanation for motion. And Ptolemaic motion was not uniform, so it violated certain philosophical principles. So this critique of Ptolemy was important in moving forward. Here we see on the left one of the diagrams of the eye as an optical device and a recreation of what Alhazen might have looked like. That's the westernized name for him. And a translation of his optics book from 1572. Al-Tusi, from the 13th century, wrote extensively on many scientific subjects, as well as on medicine, theology, and philosophy. He oversaw the construction of an observatory and a major library, much like the House of Wisdom from centuries before. He also invented a clever thing called the Tusi couple, converting circular motion to linear motion, and then he generalized this into 3 dimensions, so creating a new model of planetary motion. This turns out to be the same device used by Copernicus independently with no knowledge of Al-Tusi's work. With Ibn al-Shatir, we have the idea of designing and creating philosophically acceptable models going into decline. And for some reason, it seems like the Greek tradition is lost. And we're trying to understand now the distinction in science between something that's a good mathematical model and something that represents the physical world. So, through this span of time, although it was there at the beginning, by the end of the Islamic period, something from Aristotle's been lost, the idea of using observations and models to describe the physical world as it really is, which after all is the goal of science. In this time, we see the rise of observatories for the first time. Islamic astronomers, like their Chinese counterparts, began the tradition of fixed observatories, long periods of routine observation, carefully kept records, and specialized instrumentation. We've seen the construction of a gnomon, or a primitive sundial, 5 meters high in the year 800, and a similarly sized quadrant. Now, some observations only needed to be made once. For example, simultaneous observations of lunar eclipses were used to determine the longitude difference from Mecca for the celebration of the festival, and that only has to be done once. They also experienced some technical difficulties, falling into the trap of thinking that a bigger instrument is always a better instrument. There was one sextant built in these times that was 20 meters in diameter, and its sheer weight was sufficient to shift its alignment as the foundation settled, so it wasn't a very good instrument. There were more famous later observatories where the scale was smaller and the instruments were more reliable, at Samarkand and Constantinople. Here we see instruments built by Ulugh Beg, now from the 15th century, a grandson of Tamerlane. He created a monumental observatory, the ruins of which still remain, in Samarkand, which is currently Uzbekistan, which has a sextant and other instruments. The mural sextant is enormous. You can walk through it. He also made a major new star catalogue, the first since Hipparchus in the 2nd century BC, with 1,000 high-precision positions. It was completely unknown in Europe. They also built big in Samarkand, and that was not always the best way to go for the most accurate observations. And that's the end of this topic.